we basically, I already did this over here. So basically, for n different stages, it is 1 by n, and this is what the expression for delay, that's what I wrote over here. Okay, so this is what you need to apply given a particular circuit. Now the thing is that you are a designer. You're not going to play with these symbols, right? The symbols mean very little. As a designer, what lesson I can learn from this? And that's what we'll show. That if I have a Boolean network, how am I going to size the transistors such that the delay will be minimum? That's the goal. Okay. So our goal is that given a Boolean network, how do I size the PMOS and NMOS transistors such that the delay is minimum? So this is what the task of the engineer is. The goal of the engineer is to basically design circuits which will run fastest so that you get the best speed out of it, best performance out of it. So that being the goal, let's see that how we can apply these formulas, these simplified formulas, how we can apply to achieve that goal. We'll do that for a few examples. Okay. So the first example consists of 3 NAND gates. So we have 3 different NAND gates. All 3 are 2-input NAND gates. So this is my C in and this is my C out. So C out is going to say 108. It may be driving a long bus or something like that. You extract out the capacitance, and that happens to be the 108. And the input capacitance is equal to say 4. Now the question is that what is the size of PMOS, NMOS of each of these 2-input NAND gates? How do we find out what they are? And that's the goal. So as a designer, you're trying to minimize the delay between A and B, minimize by sizing the transistors of NAND gates simultaneously. Now this is a small example you can do by hand, and that's what I will show you. But when you go to companies, you may have to solve a very large problem. Then there are some tools, polynomial solver tools, which helps you to do that, the simultaneous sizing of the transistor. So let's see what we do here. So G1, this is a G1, this is G2, this is G3. So these are these G's are, so let's put a prime here so that you don't get confused. So these are the symbols for the gates. So G1, which is equal to G of G1 prime, is equal to n plus 2 by 3, which is 4 by 3. G2, G of G2 prime is 4 by 3. And G3 is G of G3 prime is 4 by 3. So each of these gates has a logical effort of 4 by 3. So the capital G, which is G1, G2, G3, is equal to 4 by 3 to the power 3, which is 64 by 27. And that happens to be equal to 27, 64 by 27, 2.37. Okay. So that's the value of the G. There is no branching. No branching. So B is capital B is equal to 1. H is equal to C out by C in is equal to 1/8 by 4, which is 27. So we can calculate F. So F is equal to GBH, which is equal to 2.37 multiplied by 27. This is equal to, it's close to 64. 63.99 into 64. So which means that the optimal value of path effort per stage is given by F by 1/3, which is equal to 4. So each stage has to have a path effort of 4. So F1 should be equal to 4, F2 should be equal to 4, F3 should be equal to 4. So if I know this, I can calculate the value of D. D is equal to N multiplied by F by 1 to the power N, where N is the number of stages, plus P1, P2, plus P3, the parasitic capacitances of each of these gates. So N is equal to 3, F by 1 by N is 4, plus P1 is 2, P2 is 2, plus P3 is 2. So 12 plus 6 is 18. So 18 tau is the process constant, so 18 tau. So if you are using 130 nanometer process, then we'll have 18 multiplied by 8.6 picosecond, which is equal to whatever it is. And if you use D is equal to 45 nanometer process, then it will be 18 multiplied by 3, which is 54 picosecond. So this is how you calculate the delay without doing any simulation, just using simple formulas like this. But you have not still answered this question. How am I going to find out from this what should be the sizes of the PMOS and NMOS transistors? So in order to do that, we'll have to now extrapolate the value of the capacitance here so that the stage effort is 4. Similarly, we'll have to extrapolate the value of the capacitance here so that the stage effort is 4. We know the capacitances are here and here. So the question is, what is the value of this? If I know the value of this, then I can say the size of this and the size of that. So this is how we try to derive the size of the transistors. How do we do that? So we use this simple formula. We had C out by C in is equal to H in our original formula. That is this to this. Now if I call this C1 and this is C2, the question is that what is the value of C out by C2, which will be equal to H2, or rather 1, 2, 3, H3. Now, from this